Okay, so in this video, we're going to go ahead and solve some exponential equations with logarithms. So we're going to pick a particularly nasty exponential equation. We'll do 3 times 4 to the power 2x minus 1 is equal to 5 times, let's go with 3 to the power x plus 2. The reason why this is a very ugly problem, and I'll put these in brackets rather than using dots. The reason why it's a very ugly problem is because of the fact that, well, none of the bases are the same. There's no chance of me dividing out or combining these things in any other way. So I know I'm just going to have to bite the bullet and take the logarithm of both sides. So I'm going to take the logarithm of both sides. Now I can choose to take the logarithm with a particular base. So I can do a logarithm base 4, I can do a logarithm base 3. I'm going to choose to do a logarithm base 3. Maybe pause the video for a second and think about why. Okay, if you've unpaused the video, the reason why I'm taking a logarithm base 3 is because it's actually going to make this 3 work out really quite nicely for me. And you'll see what I mean once we get there. So just the notation at first, I'm writing logarithm base 3 equally for both sides. Because what I do to one side, I must do an equivalence to the other to maintain equivalence. So now I've got the product of two terms inside a logarithm. Well, I can break that up into a sum of logarithms. So this is logarithm base 3 of 3 plus logarithm base 3 of 4 to the 2x minus 1. And this is equal to logarithm base 3 of 5 plus logarithm base 3 of 3 to the x plus 2. Okay, great. Now, these logarithm base 3 arguments are awesome because what's the exponent needed to raise 3 to 3? Well, that's 1, so they cancel. That's going to leave me with 1. Now, for this next one, this exponent is going to come down and in front. So this is going to become 2x minus 1 times logarithm base 3, 4. On the other side of things, I'll still have logarithm base 3 of 5. But now these 3's, logarithm base 3, 3, well, what's the exponent I need to raise 3 to become 3 to the x plus 2? Well, that's just going to be x plus 2. And I'm going to have some algebra here, but now I have the variables out of the exponents, which was the ticket here. I had to get the variables away from the exponents. And now they're both down as regular multiples. So I've got to combine some like terms. I think this 1 and this 2 are going to go nicely together to create a 1 on this side. I'm going to bring my variables to the left, so I'll put a negative x here, just so that way that moves. This is going to stick with log 3 to the 5. So now I have to contend with this ugly term. Well, I'm going to go ahead and expand it. So it's going to be 2x log 3, 4 minus log 3, 4. So what I've done is I've just expanded both terms in the exponent back into the original logarithm. Now, I have one term here that does not contain an x, so I'm going to move it to the other side. So if you let me keep writing, I'll have 2x log base 3, there comes the light again, minus x. And on this side, I have log base 3, 5, plus log base 3, 4, plus 1, because I still have that 2 minus 1 there originally. Okay, I'm going to have a little bit more fun here because I'll have some more work to do, but I've got to combine these like terms. Now, log 3, 4 is really just a number slightly bigger than 1. So this is 2 times x times a number slightly bigger than 1. So it's kind of like a number bigger than 2 minus 1. This is about 1x. So this is actually a pretty good estimate of what x is going to be on this side. But let's combine our terms. And I like to combine them by factoring. So I'm going to factor out the x. And this is going to become log 3, 4. Oh, I forgot that 2 because there was a 2 in that term. Well, it was a 2 in front, so I can use a property of logs that allows me to bring it back into the exponent. you might want to pause the video and figure out why that's valid. Why can I bring this back into an exponent there? Anyways, this will be -1. And then now I'm going to use another property of logs to put these things together. In fact, I'm actually just going to rewrite this as log base 3 of 3 because I can write 1 as log base 3 of 3. That's how I got it down here. So maybe that was actually a pointless step, just made it easier for me to create my ones. Okay, putting all these together with the product rule, this is log base 3. 5 times 4 is 20 times 3 is 60. And on this side, I have x log 3 16 minus, well, this is -1. So I can just write this as log 3 3 is equal to log 3 60. And I can go one further. I can combine these by subtracting. So this will become log 3 16 minus 3. Well, that's actually going to be 16 divided by 3 is equal to log base 3 60. Now I'm going to go and do something a little crazier. I'm going to try and earn myself some more room here. Hopefully you can still see what's going on. But what I'm going to do is I'm going to change the base of each of these. So I'm going to use the change of base formula. This will be x, it's going to stay up front. This is going to be the logarithm of the value, 16 over 3, divided by the logarithm of the base, log 3. This side is going to be the logarithm of the value, 60, divided by the logarithm of the base, log 3. The reason why I do that is now I can multiply both sides by log 3. And those will cancel. That'll just mean that all I have to do is divide this by the logarithm of 16 over 3. So x is going to be equal to logarithm 60 divided by logarithm 16 over 3. Whew. And I could write that as one single logarithm if I so choose. I could write it as x equals logarithm base 16 over 3, 60. Now that is a rather ugly base to have to choose there, 16 over 3. But this is an exact value answer to this exponential problem. And that's a challenging exponential problem, demonstrating lots of laws of logarithms with a fair amount of algebra working your way through.